Hello, so in this video we'll talk about relations, properties and digraph representation. So let's start with the definition. If we have A as a finite set and we are interested in a relation that is a subset of A cross A. So what is A cross A? A cross A is a Cartesian product of A with itself. So now the digraph representation of R comprises of a set of vertices and a set of edges satisfying the following rules. So all elements of A are the vertices, all elements of R are the edges, and an ordered pair of AB represents a directed edge from vertex A to B. An ordered pair of form A to A represents a loop from the vertex A to itself. So let's say example here we have A, this is equal to A, B and C. So we have three vertices. This is A, this is B, this is C. So A and B and C. So let's say our relation is A to B, C to C. So we have this ordered pair is represented by this edge, A to B, first element to second element. And this ordered pair is represented by this loop, this ordered pair, C to C. Okay. So this is a small definition of uh, the digraph representation. Now the question comes that what is the maximum number of vertices we have and what is the maximum number of edges we have. So maximum vertices, this is should be equal to the cardinality of A, right? And actually not maximum vertices, this is always, so always true. So always the number of vertices should be equal to the cardinality of A. So maximum may not be appropriate here. What about the maximum number of edges? So maximum number of edges should be the cardinality of A cross A. Okay, so if cardinality of A is equal to n, the cardinality of A cross A, this is equal to n squared. So this is the maximum number of edges we can have. Okay, now we come to the properties. Now we know that relations have properties. Sometimes they are symmetric, antisymmetric and so on. So here is a definition. I'll quickly pass through the definition, and once we do the examples it will be more clear. So a graph is said to be symmetric whenever we have an edge from A to B. This implies if and only if an edge from B to A is also present. It is antisymmetric if an edge from A to B is present and edge from B to A is not present. It is reflexive if every edge has loop. If it is irreflexive, if no edge has a loop. If it is transitive, if a condition like this is true, if there is an edge from A to B and B to C, then for it to be transitive, the edge from A to C should be present. Inverse, digraph having all the edges as the original graph but in the opposite direction. So we flip the direction of each edge. For complement, we remove all the edges from the graph and put all the edges which were not present in the graph, all the other possibilities basically. Okay, so let's see how we can apply the actual example. So we have here 1, 2, 3. So first of all, what we'll say 1, 2 and 3. So 1, 1 is the first ordered pair. 1, 3 is the second ordered pair. 2, 2 is the third ordered pair. 3, 1 is the fourth ordered pair. And 3, 3 is the fifth ordered pair. So this is 1, this is 2 and this is 3. Okay, now is it symmetric? An edge from A to B is present if and only if. So edge from 1 to 3 is present and 3 to 1 is also present, so it is symmetric. Antisymmetric? No, because of the same reason. 1 to 3 is present and 3 to 1 is also present. Reflexive, all edges have loops, yes. Irreflexive? No. Transitive, so we never encounter this condition that we have A to B and B to C, or A to B or B to C, or A to B or B to C. So since the starting condition is false, then the overall statement is true. Remember that if we have to prove this P implies Q, then the only way this can be false is that this is true and this is false. Okay, since this is false in our case, so then the overall P implies Q is true, and we have transitivity here. So complement, remove all the edges. So we'll draw this again. So we should not have 1 to 1, we should not have 1 to 3, we should not have 3 to 1, we should not have 3 to 3. The only we can have is this guy and this guy. So this is my 1, 2 and 3. Okay, okay, this is the complement. What about the inverse? So inverse is, we just draw the same graph with the same edges, but then flip the direction. Okay, so this guy becomes this guy becomes this guy becomes this guy becomes this, and this guy becomes this. So again 1, 2, 3. So now it is easy to see that inverse is equal to itself here. Okay, this is the same as in the matrix representation. We said that the inverse is related to the transpose. So in this case, this is the transpose of this guy. Okay, okay, let's do another example. So we have again 1, 2, 3. So 1, 2, 1, 2 is this guy, 2, 2, 2, 2 is the loop, and 3, 2, 3, 2 is this guy. So 1, 2, 3, 2 and 2, 2. So 1, 2 and 3. Is it symmetric? So we have 1 to 2 but not 2 to 1. So is it anti-symmetric? We have 1 to 2 and not 2 to 1. Yes. We have 3 to 2 and not 2 to 3. Yes. And we do not even have 1 to 3. So this is anti-symmetric. Is it reflexive? No, it is not, because 1 and 3 do not have loops. Is it irreflexive? No, because 2 has loops. Is it transitive? It is not. It is again transitive, because 1 to 2 is there but 2 to 3 is not there. So our first condition is false. And again 3 to 2 is there but 2 to 1 is not there. So it is transitive. Complement. So complement is, we draw it like this. Okay, so this loop should not be there, this should be there, so this should be there too, this loop should be there, this loop should be there, and these two edges should be there. Okay, so the drawing doesn't matter here, right? So 1, 2 and 3. Now how many edges do we have here? 1, 2, 3, 4, 5, 6. 6 plus 3 is 9, and 9 is my n squared. So because 9 is 3 squared and we have 3 elements in A. Now inverse. Inverse is just the same graph. So then this becomes this becomes this, and this becomes this. So 1, 2 and 3. Okay, so this is the complement and inverse of this one. Now let's do another one. Now we have a big one here. So we have 1, 2 and 3. So we have 1, 1. Okay, 1, 3. Okay, okay. 1, 3, and we have 1, 1. This should be 1, 2. I made a mistake here. This is 1, 2. Okay, so 1, 2. Okay, 1, 3, and then 2, 1, and 2, 3. Okay, and then 3, 1, and then 3, 2, and then 3, 3. Okay, so now you can see that it has all the possible edges except the loop here. Okay, so then this means the complement we can immediately draw. Complement is just this loop. Okay, so 1, 2 and 3. Okay, okay, now we go to symmetry. Now we have 1 to 2 is present and 2 to 1 is present. 1 to 3 is present and 3 to 1 is present. 2 to 3 is present and 3 to 2 is present. Okay, so it is symmetry, and it is not antisymmetric. Is it reflexive? No, because 2 does not have loops. It is irreflexive? No, because 1 and 3 have loops. Is it transitive? So 1 to 2 is present, 2 to 3 is present and 1 to 3 is present. That's correct. So 1 to 3 is present, uh, 3 to 2 is present, and 1 to 2 is present. So that is also true. And similarly, you can check all the conditions. 2 to 1 is present, 1 to 3 is present, so 2 to 3 is also present. So it is transitive. Inverse is just we draw them in the opposite direction. So then this becomes this guy, this becomes this, and then this becomes this. Basically it's the same thing. I'm just making sure that all the edges actually do change direction, but in terms of graph it's the same thing. So this is my 2, 1 and 3. Okay, so this is it about how can we represent a relation by a digraph. Okay, so graphs are actually a huge topic, and if we can always go back to the definition, what do they represent? They represent a relation from a set to itself, and it's nothing but a subset of the Cartesian product of a finite set from itself. Okay. Okay, so this is it about graphs and their relations and properties represented by uh, a digraph. Okay, okay. Thanks for watching. Hope you like the video.